Good morning, everyone. Thank you for joining today's EAC webinar. This is Cassie Stumo. I am the marketing specialist here at EAC. Lauren Adey, our additive manufacturing specialist, will be delivering an introduction of EAC, and then Kevin Gautier will be talking to us today on how to create a 3D print with the Form 2. We are a leading commercial partner for Formlabs, bringing together our expertise of the product development world combined with the #1 high resolution and affordable desktop 3D printer on the market today. If you've never heard of Formlabs before today, you'll get a pretty good idea of who they are and then what they can offer to you in terms of 3D printing hardware and materials in this presentation. This session is being recorded unless there are any technical difficulties. Everyone will receive a replay after the webinar. So please feel free to drop questions in the chat as we go. We'll answer them after the presentation. I'll hand it over to you, Lauren, for the EAC introduction.
Awesome. Thanks, Cassie. Hi, guys. My name is Lauren. Some of you may know me and some of you may not. I'm the additive manufacturing specialist here at EAC. And for those of you that may not be familiar with EAC, our mission here at EAC is to transform the way that companies are designing, manufacturing, connecting to, and servicing their products. And you may be asking, what does that really mean? Well, essentially, we help organizations build better products faster, as well as help improve operational efficiencies. And we do this by offering engineering and design services like software and support for PTC, Creo, and Windchill, implementation and training. We also offer product and part design services, assessments, and IoT solutions to help companies define a strategy of getting products connected. And finally, the one that relates most to our webinar today, we're a commercial partner of Formlabs, just like Cassie mentioned before. We partnered with them about 2 years ago, and we offer an affordable solution that gives companies the ability to streamline their design process and make it easier to bring 3D printing in-house. So with that being said, let's turn it over to our Formlabs expert, Kevin, to walk us through some of the processes of printing with the Form 2 from start to finish.
Thanks, Lauren and Cassie. Excited to be here today and to present to everyone. So we're going to talk about a workflow on stereolithography 3D printing and introduce the Form 2. Today, you're going to really learn how stereolithography 3D printing can be used for lots of different engineering applications that demand tolerances. I'm going to walk through a few things, but just to sort of set the tone, traditionally parts are produced with something like CNC machining. And we all know that for low run production, CNC setup, work holding, and programming really gets expensive. Other 3D printing technologies like fused deposition modeling or digital light projection can make parts quickly, but not always as precise as a laser-based machine like Form 2, and we're going to look at that in more detail. After today's webinar, I hope everyone leaves understanding how the Form 2 can achieve tight tolerances, how they can produce parts with the Form 2 in a small amount of time without having to send parts out for outsourcing, and how they can reduce the cost thanks to the price of the materials and the ease of use of the printer. Again, this is a small footprint, intuitive, and easy to use stereolithography 3D printer, and we're going to learn more about what that means. So the agenda, we'll talk about me and Formlabs. I'll introduce myself and the company, what's possible stereolithography technology, how stereolithography 3D printing works. We'll go through each of our engineering materials, explain their properties and some of their use cases. And then we'll take a look at the complete stereolithography 3D printing workflow from orienting a part in our PreForm software all the way to a finished, ready-to-use part. Conclusion, and then at the end, a Q&A. Remember, drop your questions in the chat box. So an introduction to myself, my name is Kevin Gautier. I'm an application engineer here at Formlabs and actually work across 2 different teams, a channel team. That's how I work with EAC. And then I also work on our business development team with our enterprise customers. In my spare time, I mentor a Formlabs AE team. And you can see on the top right a picture here of me and some of the students actually working on a intake manifold that we're making out of carbon fiber on Formlabs printed mold. So you can see everyone here kind of using a popsicle stick to tuck the carbon fiber back in the mold before we inflate the bladder in there. I also build electric vehicles, robotic motion simulation platforms, and various other things that are electromechanical devices. An introduction of Formlabs. Formlabs really set out about 6 years ago now to fit in between unreliable, low-cost fused deposition 3D printers and industrial photopolymers and selective laser sinter 3D printers. So the current product that we sell is called Form 2, and you can see it here in the middle. It's an industrial quality desktop 3D printer. It comes with free software that we continue to update regularly and make all kinds of improvements. A wide range of materials that we also continue to update. And it's at a very affordable price point that makes it accessible to small teams and scalable for large volumes. So it's a very versatile price point at about $3,500. And again, that allows, your small business or your hobbyist to own one. It also allows large enterprise customers to scale and have as many of these printers as they need to meet their demand. So we work with a lot of different major companies out there. You might have seen a recent story on Formlabs and actually Gillette here, where we're actually doing custom razor handles. It's a really exciting story, and if you haven't seen it yet, there's a great video out there online. But our products are used by tons of enterprise customers, doing really diverse things, from everything from robotics to components of cars with automotive suppliers, surgical guides in the dental industry, and custom in-ear monitors for audiophiles and hearing aids. So just this huge range of things you can do with the Formlabs printer. And we're going to look at some of those things when we talk about each of the individual materials and their use cases later in the deck. To get started though, let's talk about what's possible with stereolithography. And what we're really talking about now is geometry, and then we'll go into tolerances. So we're going to go through a couple slides on sort of the minimum geometry the printer can produce. Hopefully this helps the audience really understand what kind of minimum features they can really produce with the printer. So this is catered towards people printing smaller parts, but we'll look at a range of parts throughout the presentation. So sort of the smallest geometry you can do, minimum supported walls of about 0.4 millimeters or 400 microns. With no support on the sides of the wall, you can do about 600 microns. You can do unsupported overhangs of about 100 microns or so. This is great for fine feature detail on character sculpts or any sort of artistic work where you don't want to add support points under small overhangs. And you can actually print an overhang completely unsupported if it's around 20 degrees. You can emboss detail at 100 microns and engrave detail about 400 microns. Reason why is because if you're trying to do a channel much smaller than about 400 microns, you'll end up kind of filling the channel, and it's really difficult to clean it out as well. So really the engraved detail needs to be a little bit more coarse or a little bit larger than embossed detail. Hole diameters, you can do holes down to about 0.5 millimeter or 500 microns. Drain holes are used in the printing process to make sure you can evacuate air pressure from a closed pocket. This is a little bit of a difficult concept to explain, but we look at it later. Either way, for a drain hole, you need about 3.5 millimeters to vent the air pressure, but then also to be able to clean out the internal volume. Picture this actually being closed on the top and this being like a cross-sectional cut. If this volume was completely closed off, then a little bit of resin would actually get trapped in here during the printing process, and to be able to wash it out, you need about a 3.5 millimeter hole. So how does stereolithography 3D printing work? First, we're going to look at an example of multiple different technologies. So we can see desktop fused deposition printers over here on the left, industrial FDM printers in the white here, desktop SLA, this is actually a Formlabs part here in gray, and then industrial stereolithography on the far right. So it all starts with sort of the raw consumables of the printer. On the left, an empty resin tank, and on the right, a material cartridge full of raw material. These each hold 1 liter of material. And this resin from this cartridge actually is going to be dispensed down from the cartridge into the resin tank when you're ready to start a print with this material. And we'll take a look at that. But regardless, you also have this build platform where the part is attached to during the printing process. And again, here's that resin tank we looked at in the last slide. And that liquid resin here has now been dispensed into the bottom of the resin tank. So throughout the printing process, the build platform is going to be moving upwards in Z, and the part is going to be being pulled out of this bath of resin. The resin is unique. It's sensitive to UV light. So everywhere this liquid resin is hit with this UV laser light, the liquid actually solidifies in place. So the laser actually bounces off two galvanometers. These are really precise angular control devices that move the laser light path around in X and Y. So one of the galvos is dedicated to X, the other galvo is dedicated to Y, and they work together to draw out 2D cross sections of the parts. What's great about this system, since it's not pixel based or grid of light based in any way, we can actually draw smooth curves with the printer, and we're going to look at how those smooth curves affect tolerances of parts in future slides. But just I wanted to set the stage for where we're going with this presentation with that comment. So remember how this laser galvo system works when we're looking at slides in the future. Once the part's finished printing, it's actually going to be supported on these stock-like support structures that will just get broken off. And we're going to look at that in way more detail at the end of the presentation when we walk through the entire 3D printing process. So stereolithography and achieving tolerances. Why is a laser-based machine the best at achieving these tight tolerances? That's the idea of the next few slides. So just a quick refresher on accuracy versus precision. When you're accurate and precise, you can make a small cluster at the target you aim at. So that's our leftmost depiction here. If you're precise but not accurate, your grouping is going to be tight, but your grouping might not be where you want it to be at your target. Accurate but not precise, you can see here we're kind of surrounding the point on the target, but our cluster is not very tight. And then neither is obviously the far right. So just a quick refresher on that. Again, accuracy is how close the measurement is to the true target value. And precision measures the repeatability of the measurement. So how consistent are you at the shots that you take? This is all relevant because it is what defines the type of fit that you're trying to achieve. So you can model in tolerances in CAD software and try to achieve these tolerances, but none of that really matters if the printer can't deliver them. So to look at the three types of fits we're going to talk about today, clearance fits where there's free movement. This would be like a pin in a hole. A transition fit where a part is held in place with some friction, but it's still easy to assemble. This is like more like a peg in a pegboard where you have to use some force to push that peg in and also remove it. And then lastly, an interference fit where there's no movement and the forces are resisted. This is like a press fit. So the second layer of this here, you can see the clearance fit. This is where tolerance zones do not intersect at all. A transition fit is where tolerance zones partially intersect, and then an interference fit is where tolerance zones fully intersect. And we can see back to that sort of peg and hole example we were using. You can see that here in this diagram where we've got our hole was the blue section, or I'm sorry, the hole is the gray section sort of in this piece of material here on the right, or I'm sorry, on the left, and then the shaft is here on the right. And you can see the two different tolerance ranges, minimum, maximum on the tolerance between the two. And remember, if we're, this is a good example here of a clearance fit, but if we were in an interference fit or in an interference fit, we'd start to intersect these tolerance zones. So we did a real world test here of a 10 millimeter shaft, peg and hole, similar to what we set up in this diagram. And with varying tolerances, what we're really looking at here is how much force it takes to remove the peg from the hole as we vary the tolerance of the hole. And you can see that data plotted across a chart here for our tough resin. We're going to look at it in two different resins, in tough and in a durable material. But what's interesting here is sort of the difference between an interference, a transition, and a clearance fit, and what the modeled in tolerances mean for those fits. So the big takeaway to take away on these slides is the sort of range that it takes to get the difference between an interference, a transition, and a clearance fit with a 10 millimeter peg and hole. So you can see it takes about minus 0.0375 millimeters on the interference fit, up to about 0.05 plus millimeters on the clearance fit to achieve these different fits. And here's a same example with our durable resin. So the ranges are all somewhat similar. It's a little bit broader with the durable resin because the durable resin's a little bit got a little bit more elongation to it. So these ranges are a little bit broader, but either way, they're all somewhat in the same range. And why this is really important is what we're going to talk about in the next couple slides, which is how stereolithography, a laser-based stereolithography machine, can actually achieve all three of these fits. And that really comes down to how the printer actually works. So you can see in this diagram here, a laser-based stereolithography printer like Form 2 on the left, where we can actually feed that X and Y galvanometer at the same time and draw smooth curves. Our point size, the laser's diameter, is about 145 microns, so 0.145 millimeters. And it can be moved in increments down to just a few microns. So it's very, very easy to vary this laser path by just very fine increments to be able to achieve larger or smaller circles here when it comes to making a pin and hole example. But yeah, it's very easy to just vary the laser path just slightly. This is very different from a printer that uses a grid of pixels like a DLP or an LCD projection printer that actually uses a grid of pixels, typically around 50 microns. So you can see what a 50 micron pixel looks like here compared to our 145 micron pixel or laser point. A lot of times companies that are making DLP or LCD based printers will advertise that their accuracy is 3 times better than Formlabs accuracy because their pixel size is 50 microns versus our basically 150 micron laser point size. What they fail to mention is that we can move this laser in much smaller increments than 145 microns, and we're going to look at how that affects tolerances in the next couple slides. But just start wrapping your head around the way that you make a curve with a grid of pixels versus the way you make a curve with a scanning to X and Y scanning laser system where we can actually really finely move the laser around. So this is the example we'll use. This is about a 1 millimeter peg. Actually, in this picture here, it's actually 0.9 millimeters. And you can see here it laid out on a grid of 50 micron pixels versus the way that the laser-based stereolithography machine like the Form 2 will draw it, where this dashed line is our tool path and the laser will follow around this dashed line. So it all kind of lines up okay on the DLP printer when you're at somewhat of an equal slice or even slice. So you can see, over here in our top in the sides and tops of the circle, we really line up with a pixel pretty well. And then you can see the software of the DLP printer is going to decide if it's going to turn a pixel on or off. So this one's going to be on. This one's probably going to be on. This one would be off. This one would be on. This one would be on. And basically what the software is doing is it decides based on how much of the pixel the part uses if that pixel is going to be on or off. So it would turn this one off, for example. And it has to make that decision around the entire part to determine, where the liquid resin is actually going to be cured. So what really happens when you vary the tolerance, remember it took about 50 microns or so to change a fit over to the next one, so a transition to an interference, for example. So we'll just increase that size by 50 microns, and you can see now we're at a 0.95 millimeter diameter peg, and now we're halfway between a pixel, and the printer has to then make a whole new set of decisions if it's going to turn a pixel on or off. But what you can see is with a laser-based machine, we can just simply increase the diameter of the tool path slightly to be able to make this slightly larger diameter peg, whereas a DLP machine is really limited by its pixel size to what sort of tolerance it can really achieve. So this is what makes laser-based very versatile. It also has another side effect, which is these sort of voxel scaling artifacts that are left in the print. Since we can move the laser in such fine increments and scan it in X and Y, much like a vector graphic versus a JPEG or a GIF, you can actually achieve a much smoother surface quality on the outside of your part. So We're looking at the exact same part, printed the exact same scale with laser-based stereolithography and anything pixel-based, so DLP or LCD-based here on the right. And you can see the scaling that's left over. These edges that are showing are basically the edges of when one of these pixels just switches over from being turned on to turned off, and it leaves a scaling effect on your part. So you get a much nicer part out of a laser-based machine. You can also achieve a much wider range of tolerances. Jumping into the materials, so we have actually 6 different engineering materials. We also have a range of sort of standard resins and also dental materials. But for today's presentation, we're going to talk about our engineering materials. So you can see them all laid out on a heat map here. If you were looking for something with the most impact strength, for example, you'd be looking at our durable resin or our tough resin. If you're looking for our highest heat deflection temperature material, you'd be looking at high temp. So highest tensile strength, rigid. So you can see how this map works. It's very convenient for a quick snapshot of what all these resins pros and cons are. And we'll go walk through each of them individually and look at some examples of some parts built in each one. So again, 6 different materials we'll talk about: tough, durable, high temp, rigid, gray pro, and flexible. Tough resin, this material is similar to ABS plastic. It was our first attempt at a higher impact strength stereolithography material, and for a long time it was our highest impact strength material. But recently we released a durable material. It's got a good bit higher impact strength now. But either way, this material is great for impact resistance. Material similar to ABS plastic. You can use it for components that are going to snap together, like you can see here. Anything that needs a pretty strong tensile strength, it's great material for those usage. And some of the things that we've seen customers do with it are jigs and fixtures in machine shops, different manufacturing components so like brackets for mounting things on their assembly lines. I've seen like vision systems mounted this way. Consumer product development, we've seen prototypes of products. TV and film production, camera and equipment mounts and brackets. I personally use this material for mounting lithium batteries in like drones and small electric vehicle stuff that I work on, kind of the RC world. It's a great material for that sort of thing. Durable material. This is now our highest impact strength material. It's similar to polypropylene plastic. It's got low modulus and high impact strength, like I keep saying. This is our only material that you could actually accomplish something like a living hinge. So you can see this is a tissue box without a mechanical hinge. Instead, this is a flex joint. So you can actually produce something that could kind of fold over on itself with this durable material. So it's popular with the packaging industry for making prototypes of packaging. Another benefit that I didn't talk about earlier was it's actually doesn't abrase itself, so it doesn't scratch itself like all the other materials that we offer do. So this is a good material for any sort of sliding joint. So you know, bushings or any sort of linear bearing bushing or yeah, any sort of sliding joint. That's why this spray bottle is such a great example, because you're actually seeing multiple parts assembled and then sliding against each other. And since this material doesn't abrase itself, those parts will last a long time. I actually print gears with it, which you can see here at the end. High temperature resin. This is a material with a heat deflection temperature of 289 degrees Celsius at about 60 psi. This is the highest heat deflection temperature in the non-metal 3D printing market, so in the plastic 3D printing market. And this material is really designed for printing over mold tools or prototype injection mold tools. Also, I've seen it used for mounting components and brackets on the assembly lines that are in really hot environments. Some other applications we've seen, so automotive under hood applications. I've actually seen high temperature resin bolted between an intake manifold and a carburetor on a like a hot rod engine with basically sensors and all sorts of data acquisition stuff sort of interfaced into that part. So it's actually seen it run on an engine before. In composites, it can be used for making molds or patterns for making composite parts. I've got a customer actually putting it in an autoclave at 290 Fahrenheit right now. Actually used for molding composite materials. We're going to do a story on that in the future. In machine design, different fluid flow testing, so like fluids flowing through hot fluids flowing through a manifold. And then in vacuum forming, you can make custom patterns for vacuum forming, custom vac bags for composite manufacturing or packaging. So lots of different options for high temperature resin. Rigid material, this is our first glass reinforced material. So it's very, very stiff. It's actually got a really satisfying ting to it. Once you finish curing it and you pull it out of the form cure, which we're going to look at later, you can kind of tap on it and it's got just this great ting to it. It's really resistant to deformation over time because of the glass fill, and it makes this material really great for printing thin wall parts. So you can see some like airflow manifolds, some prototypes of sheet metal here. We've seen it used for different enclosures for electrical devices. So connectors, enclosures, or sensor housings, and air handling again, like fan blades or manifolds, and then sheet metal prototypes of sheet metal components like you see here in the top right. Gray Pro material. This material is got a similar monomer to the rigid material we just looked at. The only big difference is it doesn't have the glass fill, so it's got a bit more elongation to it. It's very dimensionally stable, and it resists deformation over time, similar to the rigid material. Big difference though is without the glass fill, it's got more elongation, so you can actually get a little more impact strength out of it. Also, you can start to do some types of snap fits, especially ones that don't need a lot of elongation to work. So we've seen it used for similar applications to the tough resin, things like form and fit testing, prototypes of extrusion profiles, and anything that really requires long-term usage. This is why you would pick Gray Pro over tough, is if it needs to last for a long time and resist that deformation over time. Tough resin will start to creep over time, where the Gray Pro is much more stable. Flexible, this is a rubber-like material that we offer. It's got an 80 durometer. It's like a charcoal black color. Really good for compression applications. So this would be like grips on tool handles or prototypes of overmolds, making stamps for stamping ink, that sort of thing. This material does not elongate very well, so you don't want to try to sort of stretch it or inflate it. Instead, you want to use it in applications where it's going to be mostly in compression. Also works quite good for vibration dampeners as well. I've done that with it as well. So now we're going to talk about the sterile lithography 3D printing workflow. We've seen why the printer can achieve these tolerances. We've seen the materials available for the printer. Now I wanted to show everyone how you actually use the printer, and basically how you take apart from a CAD model all the way to a finished physical item. So we're going to start this process in our PreForm software, which I've got opened up here. And you can see the part we're going to work on here is this 90-degree gear case, and it would obviously have the other mating half to it, but we're just going to focus on one half for the point of this demonstration. And I'm going to walk you through sort of my mentality for how I would orient and support this part to get it ready for printing. The first step is to open a file. So that's as simple as file, open. I've already opened the file, so we're going to skip that step. The next step is to go to the printer settings and actually select which settings you're going to use while printing this part. So you can see here the printer on my network is named Unknown Loris. It's actually printing right now. It's got 5.5 hours remaining on it. So we'll just let it keep doing its thing. I'm actually printing some experimental materials right now, so that's why you see the resin tank saying unused and no resin cartridge. Long story, but typically this would say what type of resin you have in your printer, and if it's been dispensed in the resin tank. Just ignore these two for now, just because of the situation my printer is in. So you would select, for setting this print up though, we are going to select the material we're going to use, which is just a drop-down list. And in our case, we're going to be using tough. And then the version number, which you can find on your resin cartridge. If there was resin cartridge installed in my printer, these values would default to this value. It could be manually overridden, but that's just a convenience feature. Anyway, layer thickness is how thick the layers are going to be. So we're going to print this part at 100 microns thick. So you can just slide the slider over to 100, click apply. Now we've got the print set up, and we just need to go through orienting and supporting the part. We have a quick, convenient magic wand feature called one-click 3D print that will automatically orient, support, and send your part to the printer. I'm going to show you more of a professional level user's way of supporting the parts. This is our sort of easiest way. I'm going to show you the sort of better way. So first thing is, I always like to think about the design intent on the part. So where's our tolerance critical areas, and what's going to make the part look the best, and what's the sort of best compromise I can make between the two. So we have some bearings that sit in these surfaces, and then we have this mating lip here that's going to mate up against the negative lip on the other side of this part. So clearly this side of the part is our tolerance critical area. So we're going to try to put our support structures over on this side of the part where they're easier to remove and they don't affect any of our tolerance critical areas. So in the end, this part's going to end up getting angled back, and let's take a look at that here in a second. So since this is a 90-degree driven node, and I like to think the process all the way through from the beginning, it would be really nice if our layer lines ran 45 degrees through the part. So I'm going to first angle the part at 45 degrees, and now our layer lines will be symmetrical about the center line of the part, and that'll make the part look really good. What I'm doing over here on the right is just driving the slider so I can take a look at what we're actually going to be working with here. And what I'm really looking for is kind of how many islands, I like to call them islands, how many islands are there going to be, which is basically separated bodies before they get up to a part where they merge or a layer where they merge together. So this one's got about 4, so actually in this case 6, which is okay with me. We've got the part at 45 degrees already. The next step we're going to do is actually roll this back a bit, so all our support structures are on the back of this part, and our tolerance critical areas are open to the top. So if you remember back to the slide on design guidelines, we were talking about 20 degrees being a good baseline for printing unsupported overhangs. So it's usually my go-to when rotating a part back like this. So I'm going to type 20 degrees in there, which I just did, and roll the part back. So now at this point, I've got the part in an orientation that I quite like, and I'm going to drop down to the supports tab and actually generate the supports. By default, I slid these sliders earlier. By default, this is usually a 0.7 millimeters and 1 millimeter for tough resin. This is something you just have to get used to over time, but basically the idea here is the lower the amount of cross-sectional area that you're filling, the lower amount of force that's going to be applied to the part. So that means you can get away with smaller and less points, smaller point sizes and less density of them. So in this case, I have a bit below average amount of cross-sectional area. So I've actually reduced the point size down to 0.55 millimeters. And I'm going to lower our density down to 0.9 millimeters. Again, these are off the default values. Usually this is 1 and this is 0.7 for tough. So came down just a little bit due to the low cross-sectional area of this part. And now we're just going to start generating these support structures. While we do that, this slider will go by down here for just a minute while it generates the support structures. But a couple little UI things about PreForm. You can see a model list over here on the right. This is going to show all the models that are in your view, and you can actually turn individual models on or off. You can also snap around to default views using these arrows, which is really convenient when you're doing any manual editing of support structures, which is what we're about to do. So you can see those support structures are all now generated. So I'm going to come in and do a little bit of cleanup. It's a good time to do your work in PreForm instead of in the physical world. So anything you can do to assist yourself later down the road in PreForm is a good idea. So what I'm going to do in here is actually hit the Edit All button, and we're going to see now a blue sphere everywhere there's a point on the part. And I'm just going to come in and clean these up. So a couple of them are on my lip here, so I'm going to remove the ones that are in the lip area. Remember, we put this at a 20-degree angle, so we don't really need these. So I'm going to remove any that affect my lip. And then I'm going to flip the part around to the back side and use these arrows we were talking about just to get into a default view. You can see these are asymmetrical, and I'm trying to make the part look really good. So I'm going to remove actually all 4 of those. And then I'm just going to come back in and add a couple more points, but more symmetrical this time. So that'll just make the part look better in the end, because there is a little bit of an artifact left over after the part prints. So you can see how easy they are to move around. Again, here's another one that's asymmetrical, so I'm just going to remove it, move this point over a little bit. And I'm just doing a little bit of manual cleanup here just to make the part look better. The next thing I'm going to do is actually, as the part goes up this wall, it gets quite vertical. Yeah, it gets quite vertical right here. So we don't really need it, the support going up this high. So I'm going to remove 2 support points on both sides here, and I'm also going to remove 2 support points here. And that just gives us a couple less supports to actually need to remove in the end. Then the last thing I like to do is I like to just browse around the part with it zoomed in pretty good, so I can see if there's any, here's an extra one. So really what I'm looking for is if there's any doubled up points, because every once in a while it'll generate a point like really close to another point. And I just don't like those because they don't clean up as easy. So I like to remove them if there are any. This model looks good. It doesn't look like there are any though. So we're just going to apply all those support edits that we made. And now we've got the model basically ready to print. Our last step is to go down to the Layout tab and choose where on the build platform we want to print the part. I like to always orient the longer dimension of the part in the orientation of the wiper, and that's because the build platform, or sorry, the resin tank is actually going to slide left to right during the peel process. And in this orientation, we have all the forces going across just this width of the part, so you know, not very much. If we were to rotate the part 90 degrees, now we've divided that sliding load across a lot more support points, and this is just a much better way to print the part. It's much more rigidly affixed this way. So that's the way we're going to print it. And at that point, we can simply save a form file of this, which would retain its material information and all of its support structures that we generated. And then we send it over to the printer with the orange print button and upload job, which I'm not actually going to do because the printer is already running right now and printing something else, and I've already printed this part. So either way, that's how PreForm works. It's quite intuitive. It's a lot of fun. You can download it free on our website and play with it even if you don't own a printer. After the part's over at the printer, we're going to print it out, and I'm going to show you, because this is a lot of steps condensed into a short amount of time, I'm going to play a video for you that shows you how you take this part from the printer and all the way to completion. So I hope you enjoy the video that I'm about to play now.
Okay, so we saw in the previous slides the resin tank, build platform, and resin cartridge. Now we're actually going to put those parts in the machine and kick the print off. So I always like to start with the resin tank. That's going to protect this piece of glass here in the printer and make sure that no resin were to drip down from, say, the build platform onto the piece of glass. So resin tank is going to go in first. And you can see here this resin tank is already filled with tough resin. I usually like to give the resin a couple swipes with the wiper just to make sure it's all stirred up. Also to make sure that the bottom of the tank doesn't have any cured resin on it, so you can see the bottom of the tank is very clear here. This just ensures your resin's in good shape and ready to be used. We'll take the resin tank and put it into the printer. Remember from the slides there's 4 little holes that the tank drops into, so you can kind of feel them. Push the tank downward and backward into the printer, and you'll kind of feel it click in. And you can see it says resin tank inserted with tough V5 resin. Next, we're going to put the wiper in. So there's a little carrier for the wiper to snap into. So we're going to find that and then set the wiper down into the slot and push backwards. You'll see that the surface goes flush here at the front once the wiper is pushed into place. Next, we'll put the build platform into the printer by lifting the release lever here, pushing the build platform into the printer until it sort of clicks, and then closing the lever. Now we'll close the printer up. We're done inside the machine, and we just need to install the resin cartridge. Remember, we're using tough V5 for this part. We selected that in PreForm. This is the cartridge. If you haven't shaken this already, you're going to want to shake this for up to 2 minutes. The other thing I like to do is check the bite valve here on the bottom and just make sure that it's opening properly. Sometimes they get stuck, and if you manually work this with your finger, you can ensure that's not going to happen once you put the cartridge in the printer. So just make sure that's opening up, and then go ahead and drop your resin cartridge into your printer and pop the air vent valve open. Now the printer is assembled and ready to print, so all we have to do is select the model we want to print, the PreForm file we sent over earlier. This is the 90-degree driven node, so we're going to select that print, then click Print Now. The printer is going to initialize. Right now it's just reminding us to make sure the vent cap is open, which we just did, and to make sure that there's a build platform in the printer, which there is. So we're sure of all of that, and we're going to push Confirm. Now the printer is going to go through a couple steps and initialize. It's also going to heat the resin up to about 35 degrees Celsius before it starts printing. So you'll see it says preparing to print. It's going to do a couple motor moves, and then the screen will come up saying we're at about 31.7 degrees Celsius. So it's going to heat up from there to 35. It's also filling the resin tank and ensuring that the level of resin in the resin tank is appropriate. So once it finishes all of these steps, it'll begin the print job. Okay, so our part finished printing, so we're going to go ahead and take it out of Form 2. And we can see what the part looks like raw out of the printer. It looks really, really nice. Now we're going to need to go ahead and wash and cure this part. So we'll start in Form Wash by popping the Form Wash open. And you can see there's actually a mount for the build platform right here. So we'll install the build platform into Form Wash. Then go ahead and start the 20-minute wash cycle. While Form Wash is running, it's going to actually agitate isopropyl alcohol and wash the part. It actually is going to reverse directions every once in a while, so alcohol flows around both sides of the part. Once it's done washing, we'll actually move it into the cure. The cure takes a little time to heat up to 60 degrees Celsius. We're going to do a 60-minute cure at 60 degrees Celsius. So I usually like to start preheating the form cure while the Form Wash is running. And we'll come back in about 20 minutes, remove the parts from the build platform, and move them into form cure. Okay, so the parts just came out of Form Wash. You'll see they're dripping isopropyl alcohol, so we'll let it drip for a little while, get most of that isopropyl alcohol off there before we take the build platform out of the Form Wash. Once it's done dripping, I'm going to go through and just start spraying a couple little areas that might hold isopropyl alcohol. We'll take a look at that in just a second once it stops dripping. Okay, so the parts have stopped dripping, and you can see they're actually starting to dry quite well. So we're going to take the build platform out and just take a look around your part. I like to see if there's any areas that might have trapped some isopropyl alcohol. Critical areas to look are usually in holes or down in little crevices. What you're going to want to do with those is make sure you blow any liquid isopropyl alcohol out of any areas where it might have gotten trapped. I use canned air for this. You don't want to use shop air typically because it might have some water or some oil in it, and that'll leave spots in your parts. So I like canned air for this. And this part has like a little areas in here where it might trap a little bit of resin, or I mean a little bit of alcohol. So we'll just go ahead and give a little spray in those sort of areas, maybe down in some of these holes. So make sure we've got all the alcohol out of all the holes. Any like tight corners like this can sort of trap a little alcohol, and you can see it probably spraying out of there right now. So I just like to go around all these sections, just make sure I'm not leaving any areas where there's liquid alcohol and resin, because once that goes into form cure, that resin and alcohol will actually cure in place. So we want to make sure we get it off there and it's dry first. So I'm going to set the build platform down on the table here, and we're going to start removing the parts. First thing I'm going to do is actually put the form wash to sleep. For part removal, everyone's got a different technique. I like the scraper that comes with the form wash actually, and my technique is to actually get under the part and then use a little twisting action to get the part to release, and you can see how easily the part comes up when you do it that way. And then I just usually work around the perimeter, and you can see the part coming up as we do that. What you're trying to do is get an area where you can actually get the scraper up under the part, just like that. And this one's released. And then we'll go ahead and get the other one released. Another note is you always want to handle the parts by the supports of the bases. Try not to touch the parts, because you will leave fingerprints in them if you touch them when they're still a little bit wet like they are right now. Once they fully harden, cure in the form cure, no worries about fingerprints anymore. So yeah, just working my way around this part right here. Form wash is really nice because it washes your build platform too, so I'm not actually touching liquid resin right now, which is nice. So I've got both parts released from the build platform, and now what I'm going to do is actually move them into form cure, which I already have preheated. So we can see it's actually been running. So what we'll do is just reset the timer once I move the parts into form cure. And I like to do this pretty quickly so I don't lose temperature. So we're just going to open up form cure and then put the parts in. Then we'll close form cure up, and it'll actually resume. Like I said, I'm going to edit the program real quick and make sure I set it back to 60 minutes. So we do a full 60-minute cure, and you'll see the temperature is coming back up. We lost about 4 degrees Celsius when I opened up the form cure, but I'll come back in a second once the lights are on and you can see what that looks like. Final step. So we've got our parts out of the form cure now. You can check them out. They look good. They're bone dry to the touch. No more worries about putting any fingerprints or anything like that in them. And now all we have to do is remove these support structures, which people do a bunch of different ways. For me, it really depends on the type of model I'm doing. For something like a larger sort of engineering part like this, really I'll just be removing these supports in bulk, and you can see if you actually fatigue them a little bit, they kind of just break right off. The only thing to really note when you're just sort of breaking them off is that the support points will scratch the part. So you should think about which way you're pulling on the supports, and maybe remove supports manually with some clippers in places that could end up dragging across the part and scratching it up. If I'm doing something really delicate and small, like a mini figurine or a character of some sort, I might actually go in and clip the supports kind of long, sort of out here in this area, and then actually come back with an X-Acto knife later and clean them all up really nicely. This really just depends on the type of model and how large it is, that sort of thing. For this model, like I said, for the most part, I'm going to be fatiguing and breaking the supports off, and you'll see kind of the process I take. So I'm going to start sort of at this end of the part, and I'm just going to clip the base so we can remove that part separately, and you can see the whole thing just fell off there, which is great. And there's just very little amount of mark left from the supports. So we're just going to go through the whole part with that sort of mentality and get all these supports off here. So I'm going to crack the base in a few places. And then I'm just going to start looking at how these supports are formed and just start sort of fatiguing a couple of these, breaking a couple of these out of the way. And it's all looking really good so far. Remember, I'm trying not to scratch the part with supports, so I'm kind of pulling away from the part as I remove the support structures. And you can see there's very little support artifact left there. I'm just going to keep removing these little sections until I've got this part completely clear of support structures. Sometimes you get little areas like this that are kind of difficult to get off, and I might just come in here with some clippers and clip, get that out of the way. And there you have it. You've got a part with all its support structures removed. This is actually really smooth already, a couple little rough edges. Like any sort of manufacturing process, you can actually go back and do any sort of secondary post-processing steps you might want to do, like sanding, which is definitely an option for a part like this. But overall, you can see really when you fine-tune your support structures, I used about, I think I used 0.55 millimeter supports on this part at a 0.9 density. As long as you're not way over supported, the supports come off the parts like really easily. Same thing will happen with this part. So now we've got the support points removed from both halves. I can show you how this whole assembly works. So here's our two halves, and you can see how nicely they sort of fit together. And you probably remember from PreForm, there's an inner and outer lip that actually has to fit together. So we can see that lip here. And if we just line everything up, it really just fits together super nice, showing how you can achieve those tolerances with the printer. Now I'm going to walk you through the rest of the assembly, and we'll put this whole gearbox together and see how it works. So a couple of gears printed in durable resin with a interference fit to make a nice press fit into these bearings, which I got to get aligned, and then just push these together. Same thing with this one. And these will actually get assembled into this gearbox. So one half here, and the other half here. So we've got the two gears assembled and they run nicely together. The second half of the gear case goes on. Nice snug fit. And we'll actually just put Plastitite thread forming screws in, which I'm gonna just start by hand. And then I'll come back and tighten up. So we got our thread forming screws in, holding the two cases together. The gears still run smooth. Last thing is our retainer cover that also keeps the gears pushed back into place. These slightly larger screw heads, so hopefully, I don't need to change bits here, but let's give it a go. Yep, this bit's gonna work. We've got a retainer plate on that's holding those gears back. You can see there are square drives down in here, which are where these two drive shafts go. So we slide a drive shaft into here, and another drive shaft into here. And now these turn each other, and this is what actuates the inside frame of the rotor casting unit that we're going to take a look at in the next slide.
All right, hopefully everyone enjoyed the workflow, and just to show you the results of this project are, so we saw the gear case get printed, and here you can see a much closer up of like how that lip fits together. Next, you can see how the rest of the nodes were put together. So there's actually 3 driven nodes in this assembly. This is the 2 straight driven nodes, and the one we just built in the video is the 90-degree driven node. All of these go together to form this rotor molding device that I built actually for that intake manifold that we saw on the first slide with the students actually. So really cool assembly, lots of tolerancing and action in this part to make, or in this assembly to make everything actually run together and everything work. And overall, really great result out of the project as well. So in conclusion, we showed you how you can achieve all 3 fits with the Form 2. how you can produce a wide range of geometries and a wide range of 6 different engineering materials. The simplicity of lastly, the simplicity of the 3D printing process. So I'd be happy to open up the floor for Q&A. Also, some next steps, a great idea is to request a sample part from EAC. They can help you with either a generic sample part or maybe a custom benchmark for your application. Either way, happy to do that. And now for Q&A.
Thank you, Kevin, for that presentation. We did have a question that came in earlier. You kind of went over it in the video, but it was how easy is it to clean up that support structure on a printed part?
Gotcha. Well, hopefully we answered that in detail. I will add a little bit more to that answer though, because it really comes down to what support size you use. If you use really large support points or way too high a density of support points, then it gets kind of difficult to remove them all. It can also mar up your surface. But as you use the printer a little more, you start understanding like what you can get away with support structures. And as you saw on the part I did, 0.55, so basically 500 micron diameter points at a 0.9 density. They came off really, really easy, and they left basically no artifact behind. So that's something you get used to as you use the printer a little bit.
Awesome, thank you. So for everyone on the call, the Form 2 is available to order today on our website. So go to eacpds.com /products /3D printing for packaging and pricing. So thank you so much for joining us on today's webinar on the Form 2. So please reach out to Lauren if you have any questions, and you'll receive a replay of the webinar shortly. Have a great rest of your day, everyone.
Thanks, everyone.